remember is that we did it through a transfer matrix. T, and the transfer matrix was written in a form where I could write it as in the limit of the small. So this was a Ising model in an external field H, and in the limit of a very small external field, we could in that case get the Ising get the transfer matrix exactly, and the goal was to write it as from one step to another in a quantum form, which is like e to the power minus IH tau. The point being that this is in a space lattice, takes me from minus beta, some classical Hamiltonian, the transfer matrix takes me from site I to site I plus 1. And compare with the quantum evolution e to the power minus IH tau for tau very small. So a small step here corresponding to a single lattice spacing here. And this becomes roughly, for small tau, 1 minus IH tau. And that is what we used as a formula for finding what the Hamiltonian is, what would be the Hamiltonian in an equivalent quantum problem, which would be similar to the transfer matrix. The Hamiltonian takes you from one time step to another. The transfer matrix in Stat.Mech takes you from one lattice point to the next. And so the correspondence between them, the T and H, were obtained from over here. That was the message of the Ising model, one-dimensional Ising model in an external magnetic field. So with that in mind, we will try to look at the two-dimensional d equal to 2 Ising model, but the much simpler problem in zero external field. So that is what what does the equivalent over here? The Hamiltonian was essentially a combination of sigma 1 and sigma 3. So the H was some combination, some alpha sigma 1 plus some beta sigma 3, where sigma 1 is the flipper, 0, 1, 1, 0 takes an up state and makes it a down state, and sigma 3, the diagonal, this. So that's the form in which we got this Hamiltonian. So now we are in the business of a two-dimensional Ising model in no external field. And what we want to do, what we want to see is what the transfer matrix looks like. So that is and all this business of being close to zero external field was because you wanted to be near criticality, and therefore, we made an identification that H was like e to the power minus beta j, This was small, H was tending to 0 because it had to be in an external, zero external transition, and the transition temperature in 0 is T equal to 0. So this was small, and the connection came through criticality. The two-dimensional Ising model, we haven't solved it. We don't know what the criticality is for the two-dimensional Ising model, but without knowing what it is, we'll sort of go ahead and see what happens. So that's the plan. So, all right. What is the strategy going to be? So here is this two-dimensional Ising model placed on, let's say, a square lattice. And the Hamiltonian, so it is partition function, sum over all configurations, e to the power minus beta h, and h will be equal to, it's a nearest neighbor Hamiltonian, so it is j summation, let me call it S, all right, Si plus 1j plus summation Sij plus 1. Okay, so that's what it is. So for the Sij, Ij is the site over here, and this chap couples to I minus 1 or I plus 1, and also to j minus 1 and j plus 1. So that's the nearest neighbor Ising model in 2 dimensions. What? Yeah. I mean, there is what? Huh? I mean, it's obviously there is all that is missing is the 0, right? I mean, this reads S0. I mean, that if I start with I equal to 0, this is S0j, S1j, plus S1j, S2j, plus so on. So that, right? So all that, I mean, if I start from 0, that's the, but I mean, yeah. So the only thing is that if I set I equal to 0, and then what I'm missing over here is the fact that I don't have a minus 1. But I can remedy that just by, I could remedy that in more correctly, but simply assume that it goes from minus infinity to essentially you are leaving out 2 spins, right? Yeah. I mean, and this, so this takes care of all the interactions in this direction. And so this is my I, and this is my j. This is the j direction. This is the I direction. So Sij, sorry, so I should have made it clear. Sij is the spin sitting at the site I, comma j. Right? So it is this Sij is the spin sitting at, so that interacts with 2 chaps here, I plus 1 and I minus 1. So I have written I, and I have not explicitly written the I, but I mean the sum takes care of it. I mean explicitly it would have been half Si minus 1 Sj plus S. sorry, this is Sij plus Si plus 1j Sij. That would be the, yeah. So, I mean, just avoiding writing, that's, yeah. But at some point, we will have to put in that half. So, all right. So, that is what it looks like. So, what is it that, what is it that is one is required to do? One is required to do sum over all configurations. Obviously, we have to break up the problem. The right way of doing it is to break it up and go ahead. So break up how? So you break it up by imagining that you have solved the problem up to this line over here. So let's say I start by summing over all the configurations of the spin up to this line over here. Then I go from this, and so let's say that I have done it. I try to do the problem line by line. I have to sum over all configurations. So every spin has to be taken into account. So how do I take every spin into account? I break up the problem by essentially do all of them on this line, then do all along this line, then along this line, and so on. So I break it up as doing it along and then proceeding. This makes it look like the situation we had in the 1D case. In 1D, we imagined that we had just a single line, and I imagined that I have done it up to this spin over here, and then I went from here to here, and over here, we imagine that it is done up to this line, let's say over here, and then I go from this line to this line. Right. So that is why if this were a three-dimensional Ising model, then it would be the same idea that I would solve it up to a plane over here, and then I go from that plane to the next plane. All right. Yeah, you can think of it that way, that essentially you are ordering it in a very specific manner. You are doing it, I mean, yeah. That you are doing X, but for a given Y, you are doing all the X, and then you are going to the next Y and doing all the X again. মানে এখানে কোনো ব্যাপার নেই, মানে তুমি যেটাকে ইচ্ছে করতে পারো। জাস্ট দ্য পয়েন্ট ইজ যে I can either I go like this or I go like this, it doesn't matter. এখানেও the একই ব্যাপার, the plane can be like this and I can go like this, the plane can be like this and I can go like this. No, diagonally not. No, all right. But then you have to imagine orienting. It's an infinite system after all. You imagine orienting the planes like this and go like that. It's just that life will be more complicated. Sure. মানে যাওয়া যায়, sure, কিন্তু মানে so all right. So what's the analogy? So what do I expect the analogy to give? What happened over here was that I reduced it to, this became a quantum problem, and it became single particle quantum mechanics with the Hamiltonian given by this. I mean, the task of calculating the partition function was reduced to finding the transfer matrix eigenvalue, which corresponded actually to the eigenvalue, solving for the eigenvalues of this Hamiltonian, single particle Hamiltonian over here. Now what is going to happen is that I have a line, and from that line to this line. So from this line to this line means, all right, this is, I can call it time-like. Going from step, let's say, which is the, so step J to step J plus 1, that if I take a decision that I will imagine that I have done all I's and on this, and then go so on. So all I's, and I go from step up to this point, everything is done, and I go from here to the next step, which is J plus 1. So it is I is done. I have to now go from J to J plus 1. So J to J plus 1 is going to be like time. Just if I were to take the 3D case, I would imagine that I do it on the surface, and this surface goes to the next surface. So this. So going from in a d-dimensional space, so if I were doing a d-dimensional Stat.Mech, this a problem which involves this Ising type of, then you imagine that you have solved it in d-1 dimensions, and then you go from one d-1 dimensional plane, quote unquote plane, I mean, to another, to the next plane. So up to this, up to this. In doing this d-1, it is just doing Stat.Mech, counting configurations and doing everything. In going from here to here, it is like making a progress in, I mean, it's like progressing in time. You can call it, I mean, what you can call it is that if I imagine that it is done up to this point, then the other is like taking a derivative, the del z, call it t, which is this. It is like saying that I'm solving a problem in which there is done up to this point, and then you time evolve this to the next step, next step, next step. Huh? Spin configurations are not evolving in time. It is because it's after all a static problem. There is no time in it. So it is just the procedure that you have adopted seems to suggest that one of the d dimensions can be likened to time. But it is not time. And therefore, you need to, call it, it is really an imaginary time. That is, if in the d-dimensional space, my components of the vector are x1, x2 to xd. And what you do is, I mean, if I were really doing a quantum problem in this d-dimension, it would have to be, it would be some field theory which would have d space dimensions, and there would be one time dimension, right? So if you were doing a quantum field theory in d-dimensional space, you would have d space, and you can imagine doing the field theory as that I progress in field theory from one time step. That is, if I discretize the time in the quantum setup, then I would imagine that you just have the space solution and at a given time, and you then go one step further and so on, and that's how you construct the whole solution. So this is the that is the Stat.Mech QFT correspondence, that it has to be, this is, I mean, your transfer matrix is e to the power minus IHT. Your Stat.Mech is partition function summed over this configuration. Over here it is, I mean, also a sum over, I mean, so infinitesimal time, I mean, this breaks up from, if I want to calculate from one time to another, the evolution, I mean, how that is, you want to know the quantum state at a time t, you imagine that this operator has been evolving, so you break up from t equal to 0, put in the time development operator, go to t equal to, let's say, tau, then from t equal to tau to 2 tau, t equal to 2 tau, and so on. And everywhere you put in this e to the power minus IHT. And that is how you get the amplitude for making the transition. You are doing the same thing, you imagine, and now you can imagine that that is the same thing that you do over here in doing e to the power minus beta h. If you think that I have done all d minus one dimensional stuff and I'm simply going in the dth direction which is left, I'm going step by step. So I choose a plane in the dth direction, and I imagine that everything up to the perpendicular, everything perpendicular to the dth direction has been done, and now I go from so at spatial point x of d, I have solved that problem, and I simply develop along the d direction from x of d to x plus some delta x of. That is the, so that is why the d-dimensional Stat.Mech problem is like a d minus one quantum problem, when it was a one-dimensional Stat.Mech problem, which is what the 1D Ising model was. It was plain and simple quantum mechanics. It reduced to finding the eigenvalues of the combination of Pauli matrices. Get the point? So so it was, but if I'm doing it in 2 dimensions, it cannot reduce to a Schrödinger equation. It has to reduce to a QFT. So it has to reduce to some kind, it will reduce to a quantum problem, but that quantum problem has to be a field theory. So the d-dimensional Stat.Mech has an analog in a d-dimensional, d minus one dimensional QFT. So that is what the point is. The 1D matrix was the 1D-izing was the easiest case where we found that the connection is with quantum mechanics, and it was very easy. This is somewhat more, obviously much more complicated, because now it is not going to be. You have to actually, as I'm saying, I have to solve the Stat.Mech problem up to this point. And then I go from J to J plus. So all the i's have been solved. All the i's have already been summed over, and up to this J, and then I go from J to J plus 1. So step 1, I need to write this Hamiltonian in a manner which makes my intentions clear. So H equal to, so what was my, this is my I and that is my J, very good. So, all right. So in a given J, so there is a part over here which is Sij Si plus 1 J. That is all happening at a given J. And so therefore, all right, I mean, this is something, a sum over, it's a sum over Ij, and you imagine that I have done this sum over Ij, and then there is also the term which is sum over Ij, but now it is Si J and Si J plus 1. My goal is to go from J to J plus 1. Therefore, I will write this term. So I write Ij, I plus 1J. So that is at, so imagine a given J, and on that given J, if I fix a J over here, then you are going to sum over all I and get that answer. But now look at this. So this is, I mean, at any J, this involves just a sum over all the I's over here. So it's the, but now this term is different. It is summation Ij Si J plus 1 minus Sij whole square let me put a minus for this as well, so that it is e to the power minus beta h. So it is e to the power minus beta h, which I write. So let me put h is this. Let me have a minus beta over here. So what I have in the numerator, what I have in this for this e to the power minus beta h, the h has it is a e to the power minus j. So the Hamiltonian is actually minus j. That's the attractive interaction over here. And so this becomes j and, yeah. मैंने उल्टो क्या ना
x square x square I plus j plus 1 ওটা 1 হয়ে যাবে এটা কিছু সামনে হবে আরেকটা কনফিউশনটা হলো 2 into si j plus 1 into si j ওটা ওটার সাথে তো একদম ক্যান্সেল হয়ে যাবে না ফার্স্ট টার্মটার সাথে
first term this product is just this. এটা তো si j plus 1. So আমি সেটাকে লিখছি as si j plus 1 minus si j whole square with a minus sign যেটা আসবে. After all, when there is a minus sign here, so আমি ওটাকে half থাকবে. Sure. I mean, সেটা তো গুণ করলে এখানে 2 আছে, I'll need a half. Sure. Yeah, certainly. So this is Sij plus 1 minus S. So here is the transfer. You are going from, this is taking you from J to J plus 1 over here. So that is a part, that is the part of the Hamiltonian which is like a movement in time, as opposed to this part of the Hamiltonian which is simply referring to a sum over all the spins which are sitting at this sum over all the i's. So all spins which are looking at the same j, all the spins which you have you just write it down, and that is what I mean, you sum over them, and that is what we have got. But then at this point you have to go, I mean, at this j you have left out the all the you imagine that, let's say, all right, these are done, but you go from j to j plus 1 and having done all the i's, so you start at the bottom. T equal to 0, you imagine all the i's done, and then you go next step by simply going from j to j plus 1, and then it's done up to the second level, then third level, fourth level, fifth, and so on. So you are having done it over the rows or whatever, I mean, over this line over here, you are moving the line upwards. Right? So it helps see. So there was this partition function. The partition function was e to the power minus beta h. That had to be done. The h is minus j, and then it is si plus 1 j, and then the other part, which is plus j by 2, and then it thank you. So e to the power minus j, h has to be a minus j because it's an attractive interaction. এইটা should have been a minus. Right, absolutely. This should have been a minus. মানে এইটার সাইনটা আলাদা হতে হবে যাতে eventually মানে এইটা becomes a plus, মানে both of them had the same sign. So if I put a minus here, and then this is minus j this and plus Sij plus 1 minus Sij whole square plus constants. So that is the thing with your and so this is summed over I, and then this is summed over all I, and now you saw everything is summed over I. I'm simply looking at H, which takes me from J to J plus 1, and then I'll sum over J. Yeah, so this is just the part of H which takes me, and this is e to the power minus beta H, and the normal notation which people use is essentially write this as e to the power L J to J plus 1. So just looking at focusing only on J to J plus 1, it is e to the power L with J comma J plus 1, and J No, sumta I এর উপর I see I হচ্ছে all those I হচ্ছে এই ডাইরেকশনে, J হচ্ছে এই ডাইরেকশনে। হ্যাঁ, তো এবারে the picture is যে আমি সমস্ত I এর উপর সাম করে নিলাম, তখন যেটা ফিক্সড এই লাইনে আমি দিস ইজ মাই এমনি করতে করতে আমি নিচ থেকে শুরু করেছি করে I arrive at some jth level, সেখানে সব করা আছে। And then I say যে আচ্ছা then I'll go to the J plus 1. So J থেকে J plus 1 এ যাব। So all the I's are মানে I গুলোকে সমস্ত করতেই হবে obviously, মানে কিন্তু আমার what I'm focusing on হচ্ছে যে আমি J থেকে J plus 1 এ যাব। So I'll bring in a notation J sigma, the spin S at I J is equal to, let's say, SI. No. Do I want it as SI? All right. So Sij, I call it a Si, that will be a sum, yeah. And Si J plus 1. So at the same point over here, if I'm, so this is J, if I'm sitting over here, it is Si. If I sit over here, it is, let's say, sigma I. The spin at the point Ij, let's say this is a specific point Ij. So spin at Ij point, I'll call it, my J is fixed. J is, let's say, 10. আমি 10 থেকে 11 এ যাব। So Sij, I call it Si. This is just a question of simplifying notations. So this chap I'll say is Si. The same chap over one step up is going to be called sigma I. মানে SI-টাও two state, it can be up and down. Sigma, no, Pauli matrix নয়. Sigma I is also a spin which can be up or down. ঠিক আছে। হ্যাঁ, একটা লাইনে এগুলো হচ্ছে SI and in the next line ওই I এর corresponding যে স্পিনটা সেটা হচ্ছে সিগমা I। কোনটা? এইটা এটা জাস্ট নোটেশন হচ্ছে যে দেখো যে jth I am looking at the jth level, ঠিক আছে? jth লেভেলে আমি এই there is a spin S1J, S2J, S3J, S4J, S5J। তো সেইটাকে আমি ওই জেটাকে সাবট্রেস করে তাকে জাস্ট SI বলছি। হ্যাঁ, এন্ড যেহেতু আমাকে এখান থেকে এখানে যেতে হবে, ইন দ্য নেক্সট ইয়ারটাতে আমি আবার আইটাকে মানে জেটাকে সাবট্রেস করে দিয়েছি, কারণ আই নো ওয়্যার আই এম গোয়িং টু J+1 and I'll not call it S। হ্যাঁ, so গোলমাল যাতে না হতে পারে, I won't call it S, I call it sigma। হ্যাঁ,
ওখানে কমা হবে,
হ্যাঁ
ওখানে কমা হবে, তাহলে আমরা ওই একসাথে হয়ে গেছে যে এসআই
I see. All right, good. So done. So a spinটাকে is being called SI আর পরের লেভেলের স্পিনটা is being called sigma I। মানে SI can be up +1 -1, sigma I tau can be +1 -1। So going from here to here involves a Pauli matrix। এইখান থেকে আমাকে যদি এইখানে যে this is a two-state system, plus minus, AO plus minus, so এখান থেকে এখানে যেতে গেলে আমার একটা পাউলি ম্যাট্রিক্স লাগবে।
হ্যাঁ, মানে এখানে সাইডে কনফিগারেশন তো আপ ডাউন, তো এখানে আপ ডাউনই হবে কি ওভারঅল?
ইয়া,
তো পাউলি ম্যাট্রিক্সটা কি থাকে হলো এটা পাইয়ে সিগমা এক্স স্কয়ার সিগমা ওয়াই স্কয়ার মানে কি করতে হবে?
মানে on at this particular I can go, I will be going, এটা can be up or down। হ্যাঁ, আর এই পার্টিকুলার এই একই জায়গায় এই স্পিনটা সেটা ক্যান বি আপ অর ডাউন। সো ইউ সি যে হোয়াট ইজ গোয়িং টু কাম ইন হচ্ছে যে এইটা আপ ডাউন ক্যান বি, মানে এটার আপ ডাউন, বাট এটার আপ ডাউন ক্যান এখানে রিকোয়ার বি ডাউন আপ। So they are going to come through the sigma X, which is 0, 1, 1, 0, which can take a up state and make it a down state. Huh? So identity sure, কিন্তু ডাউনও হতে পারে, সো তার জন্য আমাকে সিগমা এক্সট্রা লাগবে।
আচ্ছা, দুটো পসিবিলিটি,
রাইট, ইয়া রাইট। So what I'm after is that what I'm the point that I want to make is that you can see that at every this fixed I, at every I will need a Pauli matrix. And therefore I will have a whole set of Pauli matrices. To go from here to here, to go from here to here it will be a whole in an infinite number of Pauli matrices sitting along this line. So the Hamiltonian will involve for the one-dimensional Ising, the Hamiltonian was simply a spin in an external field. It was just as I had written sigma 1 and sigma 3 combination. It is now again sigma 1, sigma 3 combination, but an infinite number of them, a separate one at each point. And therefore you have a many-body theory. Yeah. All the Pauli matrices are coupled in this direction because they have a spin sitting over here. This spin is coupled here, to this, and this. So that exists, that I can't take away. So it is a coupled, and then it has to go forward in time. So it is a problem where a whole set of sigma matrices are sitting on this line over here and time developing. Right? So the two-dimensional Ising model becomes like a one-dimensional quantum problem, but not a quantum, it's a quantum field, because it's a many-body quantum system which you are having to look at. So that, and you can imagine now, it would be the same if I were to do a 3D system. I would have to take a plane and then plane to plane. You do everything in this plane over here, and then you go one step. So this step is time-like, and the plane is space-like. Everything was space-like before. But I take this point of view, and d-1 dimensions are space-like, and one of them is time-like. But it's not time-like. It's not, therefore, it is x equal to I. The x has to be written as it. Yeah, it is not a Minkowski metric, it's a Euclidean metric. Yeah. So no. Sure. All right. So that's the trick. And all right. So this is what this should be clear. That all this question of the Stat.Mech QFT equivalence is based on this picture over here. So now it's a question of how do I construct? How do I actually do it? All right. It's all, the game is entirely in this L j to j plus 1. Right? You imagine that you have done the I sum, and I'm going from j to j plus 1. So I have called this as an Sij as Si, and in the next row it is sigma I. My Hamiltonian was over here. About this part, I have nothing to say. When it is, I'm looking at L, whatever, it's e to the power. The transfer matrix is this e to the power L. So that. All right. Now, this part over here is, see, notice that why this notation? So that in this j to j plus 1 business, this is sigma I and this is Si. Right? Done? So you see this H, as I've written it, really this L is the H over here. There is no, the general notation No, all right. I mean, this followed the way I was doing it. If you read the generally literature would put it like e to the power L rather than e to the power minus beta. Because I mean, this looks very much like a Hamiltonian. Therefore, you don't really, yeah. You start with you started with a Stat.Mech, not with a Hamiltonian. It was the energy expression, and then you worked yourself up to. It's simply because that you want to reserve the Hamiltonian for a little later. That if I say that this is the Hamiltonian, then when the Hamiltonian really comes in, then I don't have a word for it or notation for it. So it's generally, I mean, you'll see it in a minute why it is preferable to write it instead of JJ. Fine. All right. So, but now what is it? I have called this. So I look at that part, and that part, the first term is simply j by 2, and then it is summation I, and it is sigma I minus Si square. All right. So that's this term over here. And then I have that term, then other term over there, which is all in, I mean, yeah, it is a combination of it's a combination of this Si and sigma I. The Sij's are this the Sij's are the Si's that you see over here, and then you have this sigma I's over here. And but now I have to, if I'm talking about the in this J2 J plus 1 business, just get the notation correctly out of the way. I is the thing over here, and I have this. So you, all right. So what it should be is that it would be Si sigma Si sigma I Sj sig. Si plus 1. Yeah, right. That is the other part is there is a Si. I have a minus J, and then I have a Si plus 1. This is for J, and then I have a sigma. So there has to be a sigma I plus 1, right? Right? In the level J, I have to sum over Si. This is a sum over Si for all the I's. Nah? So for all, sum over all I's, and then I have to go from one J to the other J. I'm looking at this part of the problem, right? I'm looking at this part of the problem from this J to J plus 1. So in this, the sum over I involves the SS. And in this, the sum over I is the sigmas. সেকেন্ড টার্মটা তো মানে পুরো জিনিসটা তো এইটা না, পুরো হ্যামিল্টনিয়ানটা হচ্ছে এইটা প্লাস এইটা। মানে এখানেও তো it is I এটাও তো I এর উপরে sum. এটা তো is see this is all at the same j and the partition function would require you to sum over all j's, right? So but this is a therefore this part, if I use a notation where this I'm calling Sij as Si, then this is Si plus 1 at the jth level. All right. But at the next level, the spins are sigma I. That's a different, I mean, the whole Hamiltonian, no. The whole Hamiltonian is e to the power, the whole partition function is e to the power it is Sij plus 1 plus Si plus 1 j. রাইট? এটা হচ্ছে পুরোটা। এইটা নিয়ে আমি কিন্তু মাথা ঘামাইনি এখনো। I have not talked about this at all. I have simply been busy transferring eta through this this term over here. But এটা পড়েছিল, হ্যাঁ, this was there. I mean, there was for every j. Mane this is a sum over. It's a sum over ij. So I have a sum over I and I plus 1, and in this case, I'm looking at two specific j's. Right, exactly. কোথায়? এইটা হ্যাঁ, particular j. So I'm going to write everything with the notation of Si and sigma I, right? সবকিছু SI sigma I নোটেশনে লিখবো। এখন in the pura Hamiltonian is actually a double, this is j to j plus 1. What you see, the whole business is a sum over I and j Si, this plus this. So I have to, therefore I'm focusing on in this part only between going from j to j, but I has to be summed over everything. Yeah, so the I has to be summed over everything. So when I'm looking at this term, I took care of this term by writing it. So this corresponds to this over here, taken care of. But what about this? This is, I have two j levels, j and j plus 1. So over here, I have to look at summation I, Si, j, and Si plus 1j plus summation I, Si, j plus 1, Si plus 1, and j plus 1, right? This part of the action, Sij, Si plus 1j, and eventually it has to be summed over all j. But I have restricted my focus on only two j's. So only two j's explicitly, it is Si summed over all I, Sij, Si plus 1j, and it is Si, j plus 1, and I plus, yeah. This is all those which are on the j plus 1th level. And this is only the coupling along the, see, the coupling along this direction has come in this term over here. ঠিক আছে, ওই ডিরেকশনের কাপলিংটা এর মধ্যে দিয়ে এসছে, কিন্তু এই ডিরেকশনেও তো ওরা কাপলড, আই ডিরেকশনেও তো কাপলড, তার তো এনার্জি আছে। So মানে যে, since I'm looking at J and J plus 1, J তেও সমস্ত I কাপলিং গুলো থাকতে হবে, J plus 1 এও all the I couplings থাকতে হবে। And I মানে J থেকে J plus 1 এ যেতে যে কাপলিংটা, সেটা has been taken care of by এই টার্মটা। বুঝেছে? হ্যাঁ, বুঝেছে? ঠিক আছে। So that is why I have to have a SI, I plus 1, sigma I plus 1 summed over all I. এই পার্টটা জাস্ট থাকবে। And this is where the, মানে this doesn't change with what I do. I mean, but this is going to be causing changes. Yeah. So now what? Now you see that the action which is in that first term over here says that all that matters. So this is this L J to J plus 1. I mean, this is what this L is all about. This is all sitting in the top of the exponential. That this is what, just focusing on J to J plus 1. All right. So you notice that the different L's that I can get are going to be determined by how many, I mean, why the question of this notation. Over here, let's say spins are S. This is level J. This is level J plus 1. Over here, the spins are sigma, right? By definition, that is what I have made. So this says it contributes only if there is a flip. So that's the vital, that's the reason for all these manipulations over here. That from spin, the variable is now become a spin flip. Yeah. Right. So it's a question of spin flip, and therefore I can write the contribution to this term over here entirely. So now what is the transfer matrix? The transfer matrix from J to J plus 1 has to be this EL J to J plus LJ J plus 1. That's the transfer matrix. So the transfer matrix is going to depend on, I mean, there is a sum over I mean, all this doesn't really, I mean, care about, it gives you the same energy all the time. But this one, at every site, I have to focus on the flip. Yes, every site I need to look at the flip. All right. So I will record configurations by saying 0 flip, 1 flip, 2 flips, and so on. So my counting is no longer by the individual spins, but just by, because this is, whatever you do, that's always going to be the same answer. They don't care. But this one is the changer. And therefore, my language changes to spin flip. So, all right. All right, that's the combinatorics that comes. Yes, right. Yeah. Yeah, right. Yes, right. Sure, absolutely. So, but the energy, the magnitude of the contribution is determined by this term over here. How many times have you flipped this spin? So if I'm looking at this object, then L, J plus 1, 0 flip is simply e to the power, the contribution is e to the power minus j si plus 1 plus sigma I plus 1. So that's the contribution to L. If it is one flip, so one flip, it means that you pick up 1 minus 1, so 4 from here, so the cost is 2j, right? And this should have been a plus, right? This is which is a plus and which is a minus. This is a plus and that should be a minus. When I it's e to the power minus beta. So L j plus 1 flip will have e to the power over here minus 2 beta j, and there should have been a beta over here, and then the same factor that I see over here. And the degeneracy of that would be n. Right? Yeah. And then the next flip is Lj plus 1, which is going to be, you have flips into, so there will be, right. So this is, if you have n flips, then this is equal to e to the power minus 2 beta j to the power n. Yeah, this is, I'm just counting the LR. I'm not calculating the partition function. I'm just looking at the e to the power L and what is L. Yeah, I'm simply looking at the degeneracy factors would have, when I'm in the business of calculating a partition function, I'll need the degeneracy factors. But here it is just a question of going from j to j plus 1, what does e to the power beta, e to the power L look like? So, or rather, what does the matrix elements, what do the essentially matrix elements of L this look like? So it's, so 0 flip, 1, and therefore Now comes the, all right. So up to now, I mean, all right, we have come some far, and this maths is, that's the maths part of it. Now one has to, again, to take the next step, one has to understand that, see, my desire is to write this as the transfer matrix from Tj to j plus 1. I want to write it as some e to the power minus h. Let's say I have taken that as some e to the power minus h tau. Right? That is my, the goal is that what Hamiltonian would actually give you the, now I know that this transfer matrix in the, if there is this Hamiltonian thing, then it has to look like this, and this is for small, sorry, this is for one infinitesimal step. So it has to be, so if that is the infinite, then it has to be like 1 minus tau h. So the matrix elements that I have been looking at over here, this e to the power L, should, if I'm in the business of finding the corresponding Hamiltonian, then I have to compare with this 1 minus tau to the power h and figure out what kind of a Hamiltonian would lead me to this. All right, so that's my next business, that I have I know that the transfer matrix looks like, I mean, for a small evolution, it looks like as tau going to limit all this in the limit tau tending to 0. So tau tending to 0, making this very, so what is tau tending to 0? Tau tending to 0 has to be this separation, I mean, essentially saying that j to j plus 1 is very small. So the matrix elements of this would be 1 minus tau h 0 flip. So I'm looking at the matrix elements of this quantity over here. Then it has to be minus tau h 1 flip. All right. So if it is h1, if it is tau h1 flip, if I whatever for 1 flip, if I write it as minus tau times h1 flip, then for n flips, it has to be tau to the power n times h1 flip. All right. So this is, I want what this will become is that for n flips, I have to write this as 1 minus something. I have done n flips, and I want this to be written as this quantity over here. So tau tending to 0, I know that it is 1 minus tau h 0 flip. So that corresponds to that's the t0 1 minus, that will correspond to if I have 1 flip, then it is going to be, I mean, you don't have, no matrix element comes from the 1 because there is 1 flip, and therefore you are going to be minus tau times h1 flip. So 1 flip here, the rest are. That's the one flip configuration. All right. Now you have, if you have two flips, then and so this has an energy which is like, let's say, one flip costs you some 2, right, 2 beta J. N flips will cost you 2 N beta J. Huh? So, but it is all in the exponential. So if this, I mean, there is this power n in the exponential. So if this looks like tau h0 flip, and the first one looks like tau h1 flip, then the nth one is. So if I flip n times, then this will be tau. It will actually be n minus 1 or yeah, right. But this is the one which goes on increase, because it is this e to the power. So that is the n which comes in, and that is what settles this issue.
Now that power is changing. H1, H2.
But it is, I mean, that is what is essentially the matrix element. No? When you are, if you are looking at, I'm looking at the matrix elements, and the matrix elements magnitudes would be, I mean, essentially be determined by the number. It is a 2 to the power n by 2 to the power n matrix. Right? I mean, there are 2 to the power n if there are n spins along this, there are n two configurations over here, and so it is a 2 to the power n by 2 to the power n matrix that you are looking at. And in that 2 to the power, what is being, the energy levels are being determined by how many, the matrix elements are going to be determined by, I mean, so essentially you are computing matrix elements between the various 2 to the power n configuration. So so you take a Hamiltonian operator, and between, so two, you have a vector which is this large dimensional vector, and this large dimensional vector, every time you have a flip, it picks up this contribution over here, and that contribution goes to this area, and n of those flips gives you a contribution which is like e to the power 2 beta j times n. So if 2 beta j is your unit, then this n flips would make it tau to the power n. I mean, you are just asking the question, what is the energy cost? The energy cost, if there is n flips, is, I mean, energy cost is 2 to n beta j. What is the contribution to the partition function? It is e to the power 2n beta j. So the contribution to this partition, which is the transfer matrix over here, just the between which is, I mean, essentially this is, I mean, the Tj to j plus 1 is now 2 to the power n times 2 to the power n matrix. Right? Because there are these I 2 to the power, I mean, n i's sitting over here. And then there are n in this, this is I, and there is I again along this direction, and there are n sitting over here. So you can have, I mean, in the number of configurations that you can have is essentially 2 to the power n, right? I mean that it's for every one over here, there are 2. So, I mean, this is 2. Yeah. 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 Huh. Okay. Car quadratic. See, the energies every time the energy factor. I'm just looking at the energy factor, not the combinatorial. The energy factor, one flip is 2 beta j. For zero flip, I mean, this is just not there. But for one flip, you are going to pick up over here 2 times beta j. If I have 2 flips, that is 2, then it is e to the power 4 beta j. And therefore, I mean, as I go on picking up this number of flips, one flip gets smaller by a factor of, I mean, by raised to the power n. The one flip energy, the two flip energy is one flip energy square. The n flip energy is that much larger. That is the business. So, the point, the moral of the story being that it is only n equal to 0 and 1 which can contribute, which is at the order tau. All the others, I mean, essentially So if because eventually, I mean, with the point is why the tau, you see, I mean, this is essentially the going to be diagonal zero flip, diagonal matrix entry. You have it till correct to order tau. And then these are all the off-diagonal matrix entries. So they are of order tau. And I drop everything which is of order tau square. So that absolutely. Yes, right. Absolutely correct. That's. I mean, this is in this setup. That is the philosophy which is being. It is essentially what would be a weak coupling. So, all right, but I'm also almost through. The vital. So I now have look, I mean, those essentially the high temperature expansion, yes, because that, I mean, is that makes the beta small, and the high temperature expansion is somewhat easily quite easily understood. Yeah, all right. I mean, you do a high temperature expansion because But the low temperature expansion is more subtle. I mean, that has to do with, I mean, the fact that it is e to the power, actually e to the power minus 2 beta j, and therefore, I mean, what is small is this quantity over here, and one has to worry about that. In the high temperature, it is just that this exponent has become small and I can simply expand. Low temperature, more tricky. So, all right, I have got to a stage where now you see that all that you need to do to find your Hamiltonian. So the point is, what was the Hamiltonian, that what is this H over here? So this the transfer matrix is in terms of this e to the power L j to j plus 1. I know what its matrix elements are, and I want to write it in terms of this. I want to write it as 1 minus tau h, the matrix elements of this chap over here. And therefore it is in terms of everything is in terms of flips, and I know that zero flip, there is this part over here which is actually common to everybody. So that's but it is all the action is over here, and what is going to happen there is therefore that this part is going to give you a set of, on this line I. So there is the I, so this is J with all the sites I over here. And then there is this J plus 1 and all the sites I over here. There is a part which involves just the spins at this site. I mean, SI plus 1 and sigma, these spins sitting, only coupling being over here is in the ith direction. Right? So all the coupling is between the in the ith direction. So it is all right. So it is sigma. Essentially, what you have is like sigma times, if I have a matrix, it's sigma times sigma part over here. But then there is this additional part which actually, so this is in terms of Pauli matrices. If I think of this, it is like sigma 3 Pauli matrix at one site connected to the other side. So it is a sigma, the third, let's say sigma 3 Pauli matrix, I to I plus 1, that is a part of the Hamiltonian. That simply comes from here. So that simply comes from, but then there is a part which involves just the spin flip and therefore has a sigma 1. So this is like yes, the sigma z up down, sigma so sigma z I plus 1, so that's this. But then there is a sigma 1 which is the connector between, I mean, and you have a sigma 1 sitting at every site I. So there is a sigma which is the spin flip operator over here, which is this flip over here, which gives a sigma I, which has to, I mean, at every site I, there is this sigma 1, which connects you from this site to this site over here. And along the line over here, there is this sigma z times the sigma z of one spin coupled to the sigma z of the next spin. So it is like a quantum problem which has a sigma 1 part and a sigma 3 part. The sigma 1 part is uncoupled, but the sigma 3 part is actually coupled. So it's a many-body quantum system. This term over here, the role of this term is through the fact, the role of this term is very important because that is what keeps makes it an interacting quantum problem in d equal to 1. The role of this term is to give you the coupling from the time development part of it, which comes through this sigma x, taking you from here to here, that being the part which contributes to specifically to the spin flip. So that is the story. And next time, what we will do, this is what is I have not really done any calculation at all. I've just motivated that this is what it is going to be. And the next time, there are some calculational steps over here, which I will to finally write down the equivalent Hamiltonian. And then it is best to actually make another canonical transformation, 1, which makes the 1 a 3. So it is sigma 3 over here and coupled to whatever. And written in that form, it becomes easy. Just said. It becomes, if I make this a 3 and these a 1 through a canonical transformation, then you can interpret this as a quantum Ising model in an external field. Because this part is just an external, sigma 3, which would just be a field in the z direction. So that is and here is the sigmas coupling, but these are Pauli matrices coupled, and therefore it's a quantum Ising chain. So that is that is the reduction. The two-dimensional Ising model, a classical system, reduces to a one-dimensional quantum Ising model in an external field. That's the. So we'll go through. It is this Kogut. That is the best possible. It's Kogut. What was that? Physics reports, right? No. This is not the physics report. Sorry. This is the RMP, Reviews of Modern Physics, 1979. It's the lattice gauge theories. Oh. But this is in the right, absolutely in the beginning. The first few pages, because that goes on to cover. It does duality. It does But this is worked out in. All the details that I have used today is purely. No. This is absolutely pure and simple Kogut. So every step that you found, you can reconstruct by going back. So actively, it's Kogut. You might have done it for the duality problem. Yeah, right. That is where probably you have done it in the Stat.Mech. But anyway, this is excellent. It's completely readable and.